regression is a method for modeling the response variable as a function of an explanatory variable. The model can be displayed graphically by putting a linear least squares regression line on a scatter plot, and it can also be expressed statistically in the form of a linear regression equation. The best fitting regression line is defined by the linear regression equation. Here is a scatter plot illustrating the relationship of engine displacement, you can think of that as engine size, and horsepower, or power of the engine. We have modeled horsepower as a function of engine size with the linear least squares regression line. How do we find this best fitting line? We do it with the regression equation. This is the general form of a linear regression equation. The symbol y with a caret on top, which I refer to as y hat, represents the predicted value of the response variable given a value of the explanatory variable. The explanatory variable in this equation is denoted x. Note that y hat is not an observed measurement for any of our units. We denote that as y. Instead, y hat values are values that fall directly on the regression line. The b0 and b1 in this equation are called regression coefficients. These are set at specified values. Once we have done that, we can plug in any value for x to obtain a corresponding value for y hat. Then we can plot that x, y hat point to start creating a regression line. Once we have 2 points, that's enough to specify a line. For example, here's the linear regression equation that relates engine displacement to horsepower. The variable x stands for displacement, the explanatory variable, and y hat is the predicted response, power, given in horsepower. If I plug in any value for x, let's say 200, I can calculate y hat. Let me use R to do this. 45.73 plus 0.44 times 200. That equals about 134. Thus, for an engine size of 200 cubic inches, we predict 134 horsepower. If I plot that XY hat pair, 200 and 134, it falls right here on the plot. Let's try it again for a value of x of 400. 45.73 plus 0.44 times 400. That equals about 222. If I plot that XY hat pair, it falls right here. These 2 points specify a line. I drew the line before we even plotted these points, but the line I drew goes right through those points, just as it would if I plotted the points first and then drew the line. The coefficients in the linear equation are the y-intercept and slope of the line. B0 is the y-intercept. This may have no practical value when we interpret it in a research setting because the y-intercept is simply the value of y when x equals 0. And sometimes 0 is not even a potential value for the explanatory variable. B1 is the slope, and unlike B0, it is always important. The slope tells us the amount of change in the response variable per unit change in the explanatory variable. Looking back at our linear regression equation and the picture of that equation in the form of a line, we are reminded that the slope is 0.44. This means that for every increase of 1 cubic inch in engine size, we expect an increase of 0.44 horsepower. Of course, 0.44 means 44 hundredths, so there's a way to make this more understandable for our research fan club. Instead of thinking in terms of a single cubic inch increase, what about if we increase the size of the engine by 100? That would mean we get an increase of 44 horsepower. Don't you agree that this is easier to understand? For every 100 cubic inch increase in engine displacement, we expect an increase of 44 horsepower. If we look at the regression line overlaid on the scatter plot, we see that the displacement size ranges from about 70 cubic inches to perhaps 470 cubic inches. If we try to interpret the regression coefficient B0, the y-intercept, in this research context, it sounds foolish. If the engine size is 0, then we expect about 46 horsepower. It's pretty silly, right? This illustrates an important concept. We should never extrapolate beyond the range of our data. This is true whether we are dealing with regression equations, or correlation, or covariance, or any other statistic for that matter. This is a good example of why we don't do that. There is nothing to say that the relationship observed within the range of our data will hold outside of that range, so we shouldn't go there. The value of 45.73 is very important to include in the regression equation, but we cannot interpret it as a predicted response for these data. Now there's an obvious question here, and it would not surprise me if you've already asked it of yourself. Where the heck did I come up with this equation? How did I know that this was the best fitting line? Did I just keep trying different lines through these points until eventually I came up with the smallest sum of squared deviations from the line? No, there are formulas for these regression coefficients that guarantee giving us an equation that will graphically translate into the linear least squares regression line. Here are the formulas. We first calculate the slope by taking the ratio of the response variable and explanatory variable standard deviations, then multiply this by the correlation. Once we have the slope, we multiply that by the mean of the explanatory variable and subtract this from the mean of the response variable to obtain the y-intercept. Once we have B0 and B1, we can use these to write the linear regression equation and use that to create the linear least squares regression line. As usual, we don't have to do these calculations. Look at this script. I first load the data for MT cars. I'm going to go ahead and create the scatter plot illustrating the relationship of engine displacement and horsepower. Now we're going to find the least squares regression model using the function LM for linear model. The first parameter is the response variable. The second parameter is the explanatory variable. These are separated by tilde, which R translates as a function of. This function will find the linear model for horsepower as a function of engine displacement. I'm going to store the results in a new object that I called lm.hpdisp, short for linear model for horsepower and displacement. You can name this whatever you want. Once I've created that object, to find the regression coefficients, I use the function COEF for coefficients. I use my new object as the parameter. This gives me the coefficients B0 and B1 of the linear regression equation. While I'm at it, I'm going to calculate the correlation among these two variables. One more cool thing before we leave this script. If my scatter plot was the last graph that I created, then after I put my new model into an object, I can use the function ABline with that new object to plot the regression line. The other two optional parameters that I've included are for the color that I want and the width that I want for my line. The default width is 1, so I'm doubling that. Here are our results all put together. The slope is 0.44 and the correlation is 0.79. These two statistics should go with a scatter plot and regression line to provide two parts of the story. The slope tells us how much change there is in the response variable for every unit change in the explanatory variable. The correlation indicates the strength of the model. What we see with this graph and with these statistics is that for every 100 cubic inch increase in engine size, we expect 44 more horsepower. We also see that we can put a lot of confidence in this model because the correlation is strong. It is one thing to know how much we expect the response variable to be influenced by the explanatory variable. That's the slope. It's something else to know the consistency of this effect. If the correlation isn't high, I'm still interested in knowing that an increase of 100 cubic inches will bring 44 more horsepower, but I won't expect this model to work as consistently because with a low correlation, the paired variable measurements will not stick so close to the regression equation. On the scatter plot, they will vary further from the line. Here's one final example. Here we have a negative relationship, so we have a negative slope and a negative correlation. Again, doing this with an interval of 100 cubic inches for easier interpretation, I see that if I increase the engine size by 100 cubic inches, I expect the gas mileage to decrease by 4 miles per gallon. This is an even stronger model because the correlation is negative 0.85. The points in the scatter plot are even closer to the regression line than in the previous model, indicating a low sum of squared deviations from the line. With the scatter plot, a regression line, the regression equation, and the correlation, you can obtain a well-defined picture of the relationship among two variables.